All right, everyone. Our homework last night, page 259, question number 1 to 3 on centripetal force, right? Which of these questions on page 259 do we need to go over? 1, 2, 3. Devin, is your hand up? No? Yeah. Number 2. Any others besides number 2? All right. Number 2 it is. It says automobile manufacturers test the handling ability of a new car design by driving a prototype on a test track in a large circle, and it gives us the radius of that circle at ever increasing speeds until the car begins to skid. A prototype car of mass 1,200 kilograms is tested and found to skid at a speed of 95 kilometers per hour. What's the coefficient of friction? Okay, a bit of a tricky question. Similar in some ways to the example that we did yesterday, but a little bit more challenging than the example that we did yesterday. We know in question number 2 that there is a centripetal force. Anytime an object is going around in a circle, there must be a centripetal force. Now, we always know that that centripetal force is caused by something else. Okay, in the case of the Earth going around the sun, it was caused by gravity. In the case of the keys going around my head, it was caused by the tension in the string. In the case of a car going around a turn, what causes the centripetal force? Yep. The tires, yeah. The tires in contact with the road. So in other words, which force is it? Right. Frictional force. Now, sometimes we don't need to bother setting the centripetal force equal to the frictional force. Sometimes, even when there is a frictional force causing centripetal force, all we have to do is say F is equal to mv squared over r, plug in our numbers and solve. That was the work that we did before this set of questions. Now we're going a little bit deeper and solving for things where we're required to set those two forces equal. There will always be something equal to the centripetal force. You're not always going to need to use it, but there will always be something that's equal to the centripetal force. All right, centripetal force equals the force of friction. So mv squared over r equals mu times the normal force. And as long as you're on a flat surface, the normal force is equal to m times g, right? The force of gravity. The masses cancel here. Although we don't need to cancel the masses because we have it. It's 1,200 kilograms. We could plug it in. We might as well to save ourselves the bother of doing that calculation involving the mass. We're looking for what are we looking for? The coefficient of friction here. Looking for mu. So let's take the g over by dividing. It becomes v squared over r times g is equal to mu. Some of you rearrange this. It becomes v squared over g times r. What difference does that make? R times G, is that not the same thing as G times R? 1 times 2 is the same as 2 times 1, right? So it doesn't matter what order you do it in. Okay, V squared over RG, V squared over G times R, same thing. V, 95 kilometers per hour, but we got to convert that to meters per second. That's 95,000 meters divided by 3,600 seconds. And what does that work out to be in meters per second? Someone's got to have that. Even? Anybody else have that? Was it exactly 26, guys? 0.38? Let's not round it to no decimal places, right? Ideally, we want to go to 3, 4, 5 decimal places. Okay, a couple is not bad. 26.38 meters per second. Let's square that. Let's square that here. Divide that by the radius, 100 times 9.81. Let's pull out our calculator to do that. Let's say 26.38 squared, divided by, let's use some brackets on the bottom here, 100 times 9.81. We get 0.71. Does that seem like a reasonable coefficient of friction? Absolutely, absolutely. Remember we did friction back in our last unit, okay, the coefficient of friction between rubber and dry pavement, between rubber and wet pavement, between rubber and concrete. I don't remember what the numbers were exactly, but they were somewhere in that range of 0.71. What units should we put with this, by the way? There are no units with coefficient of friction, right? It's a dimensionless quantity. There are no units, so 0.71 is our answer. How many people got that one? Good. Jesse? Yesterday we talked a little bit about centrifugal force. You guys remember what that was? Centrifugal with an F as opposed to centripetal with a P. Centrifugal force was that outward force, that force as it pushes you to the outer part of the circle. But what's the deal with that centrifugal force? What was kind of special about the centrifugal force, Liam? It's fictional, yeah. It doesn't exist. It's a pseudo force. There's no such thing as a force that pushes you out. So explain to me how you feel a force pushing you out when it doesn't really exist. Go ahead. Yeah, you always want to go in a straight line because of your inertia. So what ends up happening as you want to go in a straight line like this, the wall pushes you in. That's a force inward though, not a force outward, right? Yeah, that's centripetal force. The centripetal force does exist. The centripetal force pushes you in. The centrifugal force that doesn't exist pushes you out. The inward force does really exist, but that feels like an outward force. Remember we said yesterday you get struck from behind at a stop sign. Sitting there, you get struck from behind. What happens? Well, you get pushed forward, right? What does it feel like to you? It feels like you are being pushed back into your seat, doesn't it? Yeah, it does, right? It feels like you're being pushed back into your seat. That's a pseudo force, a pretend force, a fictional force pushing you back into your seat. It doesn't really exist. It's really a force pushing you forward. Okay, if there's really a force pushing you in toward the center of the circle, what's it going to feel like? It's going to feel like there's a force pushing you out toward the surface. Again, why does that happen? All because of inertia. Okay, you want to go in a straight line, but that requires the wall to push you in toward the center, creating that fictional force or fictitious force that pushes you out. Okay? Centrifugal force. Anybody ever tries to tell you about centrifugal force and how it pushes you to the outside of the circle, don't listen to them. Tell them, stand up. Tell them they're wrong. It doesn't exist. You're making that up. Here's a big thing for what we're going to do on our field trip at the end of this month. Vertical circular motion. A little bit trickier than what we've done so far. Not a lot, though. If an object goes through a vertical loop, like let's say a roller coaster car goes through an upside down loop on a roller coaster, then it still experiences a centripetal force pushing it toward the center. But that centripetal force is due to not just one force, like it was in question number 2 that we just did a few minutes ago, the frictional force, okay, or one force like gravity acting on the Earth as it goes around the sun, or one force like the string acting on the keys as I swing them around my head. But rather, when an object is going in a vertical circle, the centripetal force, which is always caused by something else, is actually due to 2 other forces. It's caused by 2 other forces instead of 1. Let's say we've got a roller coaster at the top of the loop here versus a roller coaster at the bottom of the loop. Of course, the roller coaster can be anywhere in between as well, but we're going to look at the 2 extremes, the top and the bottom. And we want to draw, since we have more than one force acting here in each of these cases, we want to draw a free body diagram for both of them. Can anybody suggest to me, first of all, what one of the forces is that acts on both of these cars, top of the loop and the bottom of the loop? Okay, the easy one. Gravity. Good. Which way does gravity always act? Good. So we're going to say the force of gravity is acting down on this cart right here. It's acting down on this cart right here. So it's acting kind of, well, from your perspective in the top cart, it's acting up, right? Because you're upside down. But it's still acting towards the Earth. In the bottom one, it's still acting towards the Earth, and from your perspective, it's down. Any other forces acting here? Well, I already told you there's one more, right, Jazzy? The normal force. Good. Which way does the normal force, let's look at the bottom one. Which way does the normal force act when you're at the bottom of the circle? Up. It acts, it pushes you up. Right? If it acted down with gravity, then what would happen to you when you're at the bottom of the circle? If the normal force acted down right here, what would happen to you? You would go down. You got 2 forces acting down, you're going to go down. That doesn't happen. We have a normal force acting up. Now, what do we know about the strength of that normal force? weaker or stronger than the force of gravity? No, it's not equal. Not usually equal anyways. It's got to be bigger. If it wasn't bigger, if it was smaller, then gravity would win and you'd end up going downwards, right? If it was equal, then what would happen? You'd end up coming out of the loop like this because the forces would be balanced. Well, except when you're exiting the loop, that doesn't happen, right? If you're staying in the loop, going around the loop again upside down, then the normal force must be bigger than the force of gravity. In other words, the force pushing it to the inward toward the center of the circle has to be bigger than the force pushing it out. What are the force acts at the top of the circle? Well, it's a normal force again. But what's the direction? This one's tricky. What's the direction of that one, Liam? Downward. Now, we don't know which force is bigger this time, the normal force or gravity. This one depends upon how fast you're moving. You'll stay in this loop, even if the normal force is weaker than gravity. But you'll also stay in the loop if the normal force is stronger than gravity. So, which one's bigger? It depends when you're at the top of a loop. Now, I'm going to draw in a red force. This is going to be much like the force of the hill when we were doing inclined planes. Remember we did the inclined planes? Right, the hills. Okay, there was a force of a gravity that acted down. There was a normal force that acted like this. And then the force of the hill. Right, remember that, guys? The force of the hill wasn't a separate force. The force of the hill was a normal force and force of gravity combined, right? We just drew it in as a third force. Not really a third force, but rather a combination of those two forces. The centripetal force, in this case, I'm going to draw in red. Which way will the centripetal force be? The force that's like the force of the hill, not a separate force, but really just a combination of the other forces. Which way is it going to act when you're at the top? Toward the center of the circle. It always does, right? If you're at the top, the center of the circle is downward. I'm not drawing it right on the diagram because I don't want to confuse you and clutter the diagram, but it acts downward. Which way does the centripetal force act when you're at the bottom of the circle? Wait, there's a force acting down and a force acting up. So which way does the centripetal force act? Up. It better act up toward the center of the circle. Otherwise, it's not a centripetal force. Right? Centripetal force always acts toward the center. It should make sense here, I think. Two forces that act downward produce a force that acts downward. A force that acts upward and a force that acts downward produce a force that acts upward if the normal force is bigger than the force of gravity. All right. Back in Unit 2, our dynamics unit, every time we saw a free body diagram, we did what? What was our next step? Every single time we saw a free body diagram. And that's what we do have here, right, is a free body diagram, two of them. What was our next step? Okay? Perfect. F net is equal to the sum of the forces. In this case, we're going to say it's equal to Fn plus Fg. Why are we not putting in Fc there? Why are we not saying F net is equal to Fn plus Fg plus Fc? I'll tell you why. Because F net is the centripetal force. F net is Fc. Right? You add these forces together, what do you get? The centripetal force, the force that pushes it toward the center of the circle. So instead of replacing it with m times a, this time we're going to replace it with mv squared over r equals Fn plus Fg. That's still m times a, right? But a is v squared over r, the centripetal acceleration. Down here, the exact same thing. F net is equal to Fn plus Fg, and mv squared over r is equal to Fn plus Fg. Now, let's just take a quick look at the signs. What's positive, what's negative, and when should it be positive, and when should it be negative. The normal force at the top of the circle should be what? Positive or negative? Negative because it's good. The force of gravity at the top of the circle should be which way? Somebody else. Oliver. The gravity at the top of the circle should be which way? Yeah, so it should be negative as well, right? The centripetal force at the top of the circle should be positive or negative? Positive or negative, Devin? Why should the centripetal force be positive? At the top of the circle, the centripetal force points down, so it's negative as well. They're all negative. At the bottom of the circle, the normal force acts, Kathleen, up, so it's positive. Gravity acts, James, down, so it's negative. And the centripetal force acts, John, up, so it's going to be positive. Good. Make sense? Listen, when you're writing the equations, don't worry about the signs. Put the signs in, positive or negative, when you put your numbers in. As soon as you put your numbers in, that's when it's important to do that. Does that make sense? Okay, we're going to take a look at one example here, and then we'll sign a couple questions for homework, and then we're done for the day. Bucket of water with a mass of 1.5 kilograms is spun in a vertical circle on a rope. The radius is 0.75. The speed of the bucket is 3. What's the tension in the rope? Let's get rid of this diagram. Don't like it. Too complicated. I got a bucket of water here going in a circle. Now, it's not actually a normal force of the track pushing, like a roller coaster track pushing in, right? It's a string. But we'll call it a normal force. It's the same thing, right? Instead of a track, it's the string, but it's the same idea. We've got a force of gravity acting down. We've got a force of the string acting down as well. Although I'm going to call the force of the string, as I said, the normal force. Just so we can be consistent. I'm going to say F net is equal to the sum of the forces. That's Fg plus Fn. And I'm going to say F net is equal to the centripetal force. It's the combination of both of these forces. We're looking for the normal force, the force of the string. Can we cancel out mass here? Doesn't appear in every term, so we can't cancel it. Mass is 1.5 kilograms. V is 3. R is 0.75. We'll worry about positives and negatives in just a moment. M is 1.5 times 9.81 plus Fn. Let's worry about positives and negatives now. The centripetal force at the top of the circle should be which way, up or down? Dustin? The centripetal force. The force that acts toward the center of the circle. The centripetal force, when you're at the top of, Dustin, you're not going to answer that. Devin's going to answer it. The centripetal force, when you're at the top of the circle, Devin, is which way? Right. So we're going to make this term negative. We plug numbers in. It's time to make it negative. Gravity is acting, Kate? Gravity always acts down, right? It's always going to be negative. The normal force is always acting down, but notice I'm not going to put a sign in for that one. How come? What did I tell you? We put our signs in when? When we plug numbers in. We don't have a number for Fn. That's what we're trying to find, right? So let's leave that. When we calculate that, we're going to find that it works out to be a negative number. All right, let's do this on a calculator. And that'll be it for us here today. So we got 1.5 times 3 squared divided by 0.75. Okay, that gives us 18. We're going to make it negative 18. I got neg 18. Let's take 1.5 times 9.81 over by adding. It's a negative number on the right side. Let's take it over to the left side by adding. I get neg 3.29, neg 3.3. We predicted that the normal force should be a negative value, right? We calculate it, and sure enough, it works out to be a negative value. Which way is the normal force acting? Down. Of course it's acting down. What other ways are going to act? The string, when you're going in a circle and you're at the top of the circle, the string isn't pushing you up. The string's pulling you back down toward the center. That's why it goes in a circle. All right? Do you see how what we're doing right now is a combination of what we've just done, centripetal force, but also stuff that we did a couple of units ago? I told you guys when we did that stuff, The net force is the sum of the forces, the free body diagrams. And that was going to carry through a lot of Physics 20 and a lot of Physics 30. That's a huge, huge skill to have, drawing the free body diagrams and then the analysis. This is just more of the same thing. This is really like elevator problems, isn't it? Fn and Fg, except that it's not ma, it's mv squared over r. Okay. Homework for tonight, homework for the weekend. Page 264, good news. We don't need you to do question number 2. Page 264, questions 1 and 3, please. Homework for Monday. Take a peek at those then. That's it. Whoops. Made a mistake here, guys. Going back to the example, made a mistake here. What did I find? I found the tension in the rope, the normal force, where? I found it at position A. What was I looking for? I was looking for it at C, right? So I found the tension at the top of the circle versus the bottom of the circle. Does that make sense what I did? Okay, so let's make a lightning fast change here. Let's change this to position C, because we've already done it at position A, right? Okay?
In the name of the Father,